I'm Robert Edmonds. This is Paul Vixie. If you came to see him, you might be disappointed because he's got a little 10-minute thing at the end. The talk we're covering today involves passive DNS. Hopefully, most of the attendees here are familiar with the DNS in general. Can I see a show of hands, people who know what the DNS is? Okay, very good. How many have read one or more DNS RFCs? Excellent. How many of you have heard of passive DNS? Okay. I'll probably skip over the introductory material as fast as possible because I have way too much material. I'd like to get to the demos, but in order to understand why the demos are so cool, you do need a certain amount of depth. So let's get started. This is the structure of the talk. There's 4 parts. I'll skip that. Okay, so the DNS maps host names to IP addresses. This is generally what we consider it to be, but in fact it's more of a more generalized system. It's basically a distributed key value system. More generally, it maps key type tuples to a set of unordered values. Yeah, so basically a multi-value distributed key value store. Excellent. Some terminology. We have clients, caches, and content. There are 3 fairly well-defined roles in the DNS. Clients request full resolution service from caches. Caches make 0 more inquiries to content servers on behalf of clients, and the results are cached. And we have content name servers, which serve the DNS records that have been delegated to them. And here's a PowerPoint diagram showing the hourglass nature of this delineation. You can see that an ISP might have millions of clients, and these clients are everywhere, phones, laptops, whatnot. And there are millions of content name servers because there are millions of domain names that people want to look up. But you have very few DNS caches. Even the largest ISPs have around 100 100 DNS caches or less. So we have this natural choke point where we can insert a monitoring application. The DNS, so I just explained we have 2 different, so we have 2 different protocols. One that the cache speaks to the client speaks to the cache, and one that the cache speaks to the content name servers. And these are fairly different semantics, but they use the same wire protocol. So the DNS is commonly considered to be, port 53, but it's terrifically complicated. So the 2 protocols are the client server protocol and the inter server protocol, spoken between caches and content name servers. Passive DNS focuses on the latter because we don't want to see client queries or give the impression that we are spying on people. In fact, what we want to do is gather intelligence about the domain name system rather than clients that are requesting that information. So passive DNS replication was invented by Florian Weimer about 6 years ago, who found a variety of uses for the technique. And the most impressive use of that to date has been in combating malware and e-crime. So domain names are so cheap as to be basically free, but infrastructure and numbering resources are not. And the sharing of that infrastructure to host multiple e-crime campaigns makes it possible to track and link malicious uses of the DNS. And just to give one example, fast flux botnets light up the passive DNS like a Christmas tree. Passive DNS replication basically consists of a number of passive sensors that listen to the packets that are generated when a DNS cache performs a lookup. The packets are then forwarded to a central collection point for analysis. After the packets captured by a passive DNS sensor are submitted to the collection point, they're then parsed and analyzed and reduced into a stream of individual records that we then permanently store in a database. And here's a picture of our DNS architecture again, where caches talk to content servers. We've taken the clients out of the picture since they're not particularly relevant to passive DNS, and we've inserted a sensor between the caches and content showing how passive DNS monitors and forwards the inter-server traffic to a collection point. And that collection point is called SIE, or Security Information Exchange. We'll cover that as briefly as we can because the main thrust of this talk concerns the database that we build based on that data. So there have been a number of different implementations of passive DNS over the years. The original is Florian Weimer's DNS logger, whose backend was initially hosted at RusCert and then at BFK. Florian's implementation uses a custom libpcap forwarder on the passive DNS sensor and a Berkeley DB database for permanently storing that data. Then we have Boyan's DNS parse out of New Zealand, which uses a fairly primitive TCP dump-based sensor and a MySQL database. And the most recent and, to our knowledge, largest implementation is in ISC's Security Information Exchange, which inserts an elaborate distribution layer between the passive DNS sensor network and the analyzers of the captured data. And we use a custom analyzer that is hardened and more advanced than the analyzers used in DNS logger or DNS parse. And our storage components have been similarly hardened and have advanced functionality for dealing with the large amount of data that we collect. There may be other implementations, but I don't know of any other publicly known passive DNS implementations. This brings us to ISC SIE, which we'll describe briefly, and only the features that are relevant to passive DNS. So SIE is a distribution network, as I said, for replicating the security data from multiple sources to private secure LANs, where the data is broadcast to trusted consumers, including ISC itself, of course. One of those types of data is, of course, passive DNS. Passive DNS sensor operators run sensor code that captures DNS traffic and periodically uploads it in batches to our submission servers. And our submission servers take care of replicating the data among physical SIE sites where the data is broadcast out in a standardized format on private VLANs, sort of a poor man's multicast. And we use a standardized interchange format called InMessage, which we use to encapsulate the data. It's an extensible binary format that we've optimized for real-time transmission on jumbo frame Ethernet. And we use this format to record the raw packets that are captured by our passive DNS sensors. And this allows us to add a good deal of metadata along with the raw messages. So for instance, instead of storing a flat stream of packets like your typical PCAP file, we embed both the query and its response, and its corresponding response into a single message, which we can then process as a unit, rather than groveling through an entire PCAP file. And we don't really need to cover data message anymore, but you can see Google Tech Talk, where we describe just that format at that URL. And this is the end of our introductory material, and we'll move on to some ancient DNS security issues and the analogs that they present in passive DNS. Unfortunately, nothing short of universal DNSSEC deployment really helps us, since passive DNS operates on a lower level than DNSSEC. So we have to be able to handle signed and unsigned data in as secure as fashion as possible. So we won't be discussing DNSSEC further. So what DNS security issues are most important to passive DNS? We have Kashpureff poisoning, which is an old, easily defeated type of DNS cache poisoning from the 90s. And we also have Kamensky poisoning, which is a particular type of DNS cache poisoning that makes use of spoofed response packets. Actually, spoofed responses in general are very harmful to passive DNS data collection. Let's see. Kashpureff poisoning is the name of a type of DNS cache poisoning that occurs when a content name server appends extra records to a response. It's particularly insidious because an attacker can poison any record in the entire DNS tree simply by running a content name server and tricking clients into looking up a DNS name under the control of the attacker. So that's very easy to do. Here's how the attack works. The attacker runs a content name server, and a client is enticed to look up a domain name under the attacker's control. And the cache contacts the attacker's name server, and the attacker's name server provides extra records to the cache. And these extra records are inserted into the cache instead of being discarded. I'm going to skip the actual example because it takes a while to explain, but the idea is that we have a malicious.example.com name, and we trick someone to look it up, and suddenly this unrelated name, www.example.net, points anywhere we want. So the blue one and the red one is malicious, the blue one is suspicious but not illegitimate. Actually, let me go back. The gray record there is the malicious one, and it gets scrubbed out by DNS caches. modern DNS caches. I think we can sort of skip this slide. We can also skip this one. And we can skip this one. Okay, now that we've covered all the background material, has been lead up to the meat of the talk, how is this particularly relevant to passive DNS? So Florian Weimer in his 2005 paper identified several problems with validating the data collected by a passive DNS sensor, but he chose not to implement protections against these problems. But we would like to fix these problems if possible. So we have the two problems in passive DNS that are sort of analogous to the two problems in this active DNS. And the problem with Kashpureff poisoning in passive DNS is that we can't see the DNS cache's internal state, so they can't recover what's called the bailiwick that the cache associated with a particular response. Bailiwick is entirely in the eye of the beholder. And this leads to a problem we call record injection. And the problem with spoofed responses is that they're treated just like normal responses by the passive DNS sensor. And a single spoofed response can poison the passive DNS database. So this kind of worries us because it makes passive DNS databases sort of an unreliable tool if an attacker explicitly wants to target a passive DNS database. So anyway, we'd like to make sure that passive DNS is at least as reliable as active DNS as far as resilience to cache poisoning goes, for whatever that's worth, in order to avoid allowing passive DNS to itself become a target in addition to the DNS. So let's move on to the protections that we've implemented on top of the basic passive DNS idea. It's actually relatively easy to protect the capture stage from spoofing. In order to make our DNS sensor at least as reliable as the DNS cache that it's monitoring, we need to capture both the outgoing queries that the cache is generating and the incoming responses that it gets back. So current generations of passive DNS only capture the responses, and they don't have the context or the state that is generated by the actual query that went out. So what we need to do is capture the outgoing queries and correlate them with the responses and verify that they fit together and form a valid transaction. In most cases, we need to verify that 9 different fields between the query and response are identical. And those are the 9 different fields that we don't have time to discuss, but basically we match them together and we can tell exactly which ones are valid, exactly which transactions are valid and which ones appear to lack the additional state to verify that they're valid. So ISC has released a tool called DNS QR that performs DNS packet capture and validates the query response pairs that are seen on the wire. DNS QR temporarily keeps each outgoing query packet in memory in a state table. And when a response packet is received, we do a lookup against that state table. And then the state table is keyed on that 9 tuple that we just skipped over. We can skip this. It's interesting, but we don't have enough time. There's blah, blah, blah. There's IP reassembly, which I won't explain why that's cool. So now that we've eliminated this spoofing vulnerability in the capture stage, we can move on to the data that is valid, or the data that has been captured and has passed all these checks, but happens to be attempting to redirect us, the Kashpureff style poisoning. So caches internally associate a bailiwick with each outgoing query, and bailiwick is sort of equivalent to the zone, but not really. It's a good enough approximation for this talk. So Kashpureff poisoning is pretty much identical between active DNS and passive DNS, and the solution is we're going to keep track of which zone or bailiwick that we expect the answer to be contained in, and we're going to discard any response records that aren't contained in that zone. And of course, nothing in the WIRE protocol indicates the bailiwick that the cache is expecting. When we're looking at a particular DNS query response pair,